This is problem 159 from chapter 12. The small washer is sliding down toward OA. When it is at the midpoint, its speed is 28 meters per second. Its acceleration is 7 meters per second squared. We want to express the velocity and acceleration of the washer at this point in terms of its cylindrical components. And we have equation 1231 for the velocity and equation 1232 for the acceleration. So what I want to do first is take this line OA and project it onto the XY plane and recognize that this is the Z direction. The radial direction is pointing in the XY plane from point A to this point here, so like that. The transverse direction is perpendicular to that, and this angle here is theta. But as the object goes from point A to point O, the radial component is along this line here, and the angle theta is not changing. If you did want the angle to change, you could hold the rope at point A and move it around like this as the washer falls, and then theta would be changing, but it's not. So theta is constant, and because theta is constant, theta dot is equal to 0, and theta double dot is equal to 0, which is going to make our two equations much easier because anywhere where there's a theta dot or a theta double dot, I get 0, so let's just cross everything out that we can when theta dot is equal to 0 and when theta double dot is equal to 0. So this whole thing is equal to 0. This is equal to 0. This is equal to 0, and this is equal to 0. So there is no transverse component for the velocity. There is no transverse component for the acceleration. Now let's rewrite the equations that we have for velocity and acceleration, and this is only for problem 159, not in general. Okay, now I just need to take my velocity and the acceleration that they gave me, so I have the magnitude, but I know the direction has to be going from point A to point O, so the object's moving in this direction, its velocity has to be pointed in that direction, and the acceleration is pointed in that direction also, provided it's speeding up, which it looks like it would be. So the rest is just taking a vector and breaking it down into components. And at this point, it really doesn't matter that it's cylindrical components that we're working with. It's just taking a vector and breaking it into components. What I want to do here is label this angle just because it's going to be convenient to have something to call this angle. So let's call that phi, but we don't have to actually figure out what that angle is. So I have a right triangle here, and the radial direction is pointed along this line. So I have a vector which is pointing in this direction. I want to take that vector and break it up into a z component and an r component. So that's just using the hypotenuse to find the two legs of the triangle, which we could do if we had this angle. We don't have that angle, but we can find what it is. So if this is equal to 3 and this is equal to 2, that would be like this triangle here, which is another right triangle because this is a right triangle. So if this side is equal to 3 and this side is equal to 2, we can find the hypotenuse. So that there is going to be the square root of 3 squared plus 2 squared, which is the square root of 13, which is 3.606. 3.606, which would be r when the object is at point A. We are not looking when the object is at point A. We're looking for the velocity and the acceleration at the midpoint. But we can go ahead and use these values because although we're not going to do it, what we're looking for here is the angle, and the angle is going to be the same whether you use 3 or 2, or the values at the midpoint would be, which would be 1 and 1.5. And now that we have this distance here, we can find the distance between point O and point A. So if this is 3 and this is 2 and this is 6, this leg here is 3.606, but when we square it, we get 3 squared plus 2 squared, which we said was 13. So we have 13 plus 6 squared, so that's 13 plus 36, which is 49. And so the square root of 49 is 7. So the distance from point A to point O is 7 meters. Okay, if I know the lengths for the 3 sides of the triangle, I can find what this angle is, but I really don't need to know what the angle is. I could say this though. Some things that I might want to use are sine of the angle, cosine of the angle, and tangent of the angle. I may not need them all, but we'll write them down just in case so we have them. So sine of the angle would be the opposite, which is the 6, divided by the hypotenuse, which is 7. So this is 6 over 7. Cosine of the angle, that would be the adjacent, which is 3.606 divided by the hypotenuse of 7. And the tangent of the angle would be the opposite divided by the adjacent, which is 6 divided by 3. And hopefully at this point you can see that it doesn't matter that we didn't look at the midpoint, because if we were looking at the midpoint, for instance, when we did the sine of the angle, that would be 3 divided by 3.5, which would still give you the same thing as 6 divided by 7. Similarly here, if we were at the midpoint, it would be 3 divided by 1.5, but you'd still get the same thing for the tangent of the angle. Okay, so now our vector, let's start off with the velocity vector. It's pointing in this direction. It has a magnitude of 28. I want to find the components, which I would do by using cosine of the angle and sine of the angle. So I have my vector pointing this way. I could try and redraw it, but it's going to be a little messy. So I have my right triangle. So I'm basically redrawing this. And the vector, the velocity vector, is pointing in this direction, and it has a magnitude of 28. And I want to break it up into a z component here, which is going to be z dot, and an r component, radial component here, which is going to be r dot. And this is a right triangle, and this angle is phi. Okay, so z dot is 28 times sine of phi, which is 6 divided by 7. So that's 28 times 6 divided by 7. Oh, but I forgot something. Okay, so this is 24, but it's not going in the positive z direction, it's going in the negative z direction. So because it's pointing in like this, that would be negative 24. And then for r dot, same thing. It's going down and inward, so both the z component and the radial component are going to be negative. So minus 28 times, this would be the cosine component. Cosine is 3.606 divided by 7. So that gives me negative 14.424. Now, if you were going to find the velocity in rectangular coordinates, you could use the same approach, but after finding the radial component, which is pointing like this, then you could use the angle theta to find the x and y components. So the z component would stay the same, and then there would just be an additional step. You would take the radial component and break it down into x and y components. Let's look at the units here. So this was meters. The speed was in meters per second. So the units for that would be meters per second. And we're supposed to do what? Find the velocity. So we can do that now. Take this velocity vector and put in the negative 14.424 for the radial component and the negative 24. Whoops, that was supposed to be a U. And this is in meters per second. We do something similar for the acceleration. The magnitude of the acceleration is 7. It's pointing in the same direction. Whoa! The magnitude of the acceleration is 7, but the length from here to here was also 7, which means if I break it down into components, I would expect to get 6 and 3.606. How easy is that? But let's just do it to make sure. So this is the magnitude of the acceleration, and so this side would be z double dot. It's going to be negative also because the acceleration is pointing this way, and this would be r double dot, and this is our angle. So z double dot is equal to negative 7 times sine of the angle, but that's 6 over 7, so this is negative 7 times 6 over 7, which just gives you negative 6. So the only thing I forgot about when I was just saying we could do 6 and 3.606 was that it would be negative, but it still worked. We got negative 6, and this would be negative 7 times cosine of the angle. Cosine of the angle is 3.606 divided by 7, so that just gives you negative 3.606. Okay, so the units are different for the hypotenuse when we look at the distance and when we look at the acceleration, but the numbers are the same. Okay, and so for my acceleration vector, I have r double dot, which is negative 3.606 in the radial direction, z double dot, whoops, which is negative 6, just forget about that, in the z direction, and the units are meters per second squared. There you go.